Bismillahirrahmanirrahim. In this video, we'll be discussing example 5.2 from Mr. Sedra's books on EDC, the 7th edition and the 8th edition. Some theory. This is the structural diagram. Main point to note is the length and width, which we'll be using in some formulas. And this is one of the equivalent circuit diagram. This is the MOSFET. And you can see we have the gate source and we have drain source. This is drain and source. And this is gate and source. Now, a theory part explaining VT, the value of VGS, that means this voltage, at which sufficient number of mobile electrons accumulate in the channel. So when we keep on increasing, this is the channel, and a large number of electrons, they get accumulated here in the channel to form a conducting channel. And when the voltage at which this form a conducting channel is called the threshold voltage, and it is represented by V small t. So this is threshold voltage you have to keep in mind. The value of VT is controlled during the device fabrication, and typically it lies in the range of 0.3 to 1 volt. Excess of VGS. So when we keep on increasing this over VT, more than VT, is termed to be the effective voltage or the overdrive voltage, and it is called VOV. So VG minus VT is VOV. This is also an important formula that we'll be using here. And when we are in the NMOS type of a MOSFET, then for VT we actually write VTN, N for NMOS. This characteristics curve is also very important. We have to keep in mind this is plotted between the drain and source voltage, that means this voltage, and current, ID current. And you can see there are two distinct regions. The blue region is known as the saturation region, where the current ID becomes constant. So this is saturation region, but when current ID is rising, then that region is called the triode region. And to distinguish these 2 points, remember that here VDS, this voltage, is greater than VOV that we saw in the discussion, that when VOV is the point where it starts saturation. So like for this is VOV, for this graph this is VOV, and for this graph this is VOV. So we can say that VD saturation, that means VD at saturation point, will be called VOB. So like these are all the saturation points. And we have already learned this, that VGS minus V threshold is called VOB. That means VG can be written to be V threshold plus VOB. So this formula we'll be using. And this is what has been shown here as the value of VG. Then another thing is that when we are using MOSFET as an amplifier, it is operated in the saturation region. So for amplifier, you operate in this region. The saturation, the drain current is constant. So we have discussed already that the drain current is constant, and it is determined by VGS. So the values of VGS will determine where this graph will get straightened. And this is the formula for ID in the saturation region. And this can be further simplified. We know VGS minus VTN is VOB. So this is a further simplified form. Just for your information, the diode equation in the triode region, this region is slightly different. So this is the equation, although we'll not be using it here. This is just for your knowledge. Now coming on to the question, consider an NMOS transistor fabricated, and these are the details: length, width, the capacitance, and permeability, VTN. So the first part, we have to find VGS and VDS that result in the MOSFET operating in the edge of saturation with ID 100 microampere. So we'll first of all tackle the part A. This graph will be referring to. And from here, we have already discussed this, that VD saturation is VOS OV, or from here VGS is VTN plus VOB. So we have to find VG, VGS, and also we have to find VDS. So desaturation is VOB. These two formulas we need to use. Now in both cases, we need to find OV first of all, because TN is given here. And now VOV we can find from the current formula. So this formula we'll be using to find VOV, because we already know ID. We also know these parameters. So let's see. These are the values that are given in the question. And first of all, Kn dash is called the transconductance parameter, which is given by mu and C, capacitance, permeability, and the capacitance. Both are given here, this value and this value. And also, to further simplify this whole term, we just call it Kn. And so when we call this a Kn, our equation becomes more simplified as here. So let's find out Kn dash first of all, putting the values, and then we'll find Kn. Using this formula, we know the width and the length given in the question. So Kn we have found 4.3 milliampere per volt square. So we'll plug in that value here. We know ID is 100 micro. So plugging in the values, we calculate VOV to be approximately 0.22 volt. So now that we have found VOV, we can find VG and VDS. Putting in the formula, VTN is already given in the question. VOV we have found from here. So it will be 0.72. And VD saturation, or VD, is equal to VOV, is equal to 0.22 volt. So this is the first part. And if you want to see in the characteristics curve, let's say with this graph, I'm just assuming, it's not given in the book, I'm just assuming that this graph is representing 0.72 VGS. VGS 0.72. And wherever it is touching the ID, let's we calling it 100 microampere. This is 100 microampere. And then this is the locus of the saturation point, or the beginning of saturation. So wherever this becomes a straight line. That is the point of our OV. So this point we'll call as OV 0.22. Now, the next part says if VGS is kept constant, find VDS that will result ID 50 microampere. Let's see from the graph again. VGS is kept constant. That means this graph will remain constant. We have to find the voltage value VD where the current will be 50. Now it was 100 microampere, it will be 50. So you see this 50 line is touching the graph at this point. So this should be our VOV new. And VOV new will be our VDS saturation. Let's see how do we find mathematically. MOSFET will now be operating in the triode region. So that is first conclusion, that from this graph, this line is touching here, and this is in the white region, and white region is the triode region. And we have discussed that in the triode region, the current equation will be different as shown here. We'll use that equation. So this we are writing Kn, already calculated Kn. We had calculated this value of Kn, and we had also calculated VOV. For the 100 microampere, VOV was 0.02. Now putting in this equation, all the values, we can find VDS. So this is kind of a quadratic equation. So we have to solve this quadratic equation. And we'll find these two answers by solving the quadratic equation. The easiest way is to use your calculator. Let me show you. So we have got the calculator. We'll use the equation mode now. Let's go to the mode switch. And number 5 is equation. So it is 5. And then this 3 is the quadratic equation. So press 3. Now it is asking the value of A, B, and C. So you know in the quadratic equation is ax square minus bx plus c. So A is 1 here, so we'll put in 1 equal sign. Then for B it is minus 0.44, so minus 0.44 equal, and then C is 0.023. So we've entered all the values. Now we need to find the two values of x. So this is the first value, 0.379. So this is actually 0.38. In the book has given 0.39, but it doesn't matter really. The other value is x2 is 0.060. So this is the second value. Okay, now this value of VDS, what he's saying here, the second answer is greater than VOB. So this is our VOB. Actually, in this case, will be somewhere here, but earlier also it was 0.022, but just 0.33 is going beyond. It is somewhere here. Therefore, this is not acceptable in this case because our VOV is somewhere here. Therefore, we reject this and we say that VDS is 0.06, somewhere here is the correct answer. The second answer is greater than VOV and thus is physically meaningless since we know that the transistor is operating in the triode region. So we are operating in the triode region, so It has to be somewhere here. Therefore, we conclude that VDS is equal to 0.06 volt. So this is the second part. Now, third part of the question says, to investigate the use of MOSFET as a linear amplifier, let it be operating in the saturation region with VDS 0.3 volt. But we are operating now in this region. And what we need to find is, if it is a linear amplifier, then the changes in ID should be linear. Find the changes in ID resulting from VGS changing from 0.7 to 0.1 and minus 0.1. Okay, so we need to find the change when VGS is changing from 0.7 to plus 0.01 and minus 0.01, so both sides. Now, it's talking about linear amplifier. So briefly, linearity refers to the ability of the amplifier to produce signals that are accurate copies of the input, that is without any distortion. Now for VGS 0.7 volt, just for my idea, I have plotted line here. This was the line we had assumed to be 0.72. So 0.7 will be slightly lower than this. So we can calculate VOG, which is 0.7 VGS minus VT. This we are using, this formula. VT we know is 0.5. That will be VOB will be 0.02. Over this line where it is touching this locus, and if we draw it down, this should be 0.02 volt VOV. And since VDS is 0.3 volt, the transistor is operating in the saturation mode. So we are here, this is the edge, and we're saying that VDS is 0.3. So obviously on the right hand side, that means the transistor is operating in the saturation region, and as an amplifier, it should operate in the saturation region. This was the formula. We know Kn, and we have just found out VOV. Therefore, the current will be 86 microampere. So for 0.7, the current should be 86 microampere. Now we need to find what will be the change in this current if we increase this by 0.01 and decrease this by 0.01. So again, we'll calculate. This was our formula for VGS. Now VGS is 0.710. We have increased this by the positive, this one. And VOV is 0.021. If we calculate from here, 0.710 minus 5. So VOV will be 0.21. So the new current, according to this formula, will be 94.86. So this was, we can say, our base reference. Now it will go slightly up to 94.8. And if we come down by 0.1, so instead of 0.710, it will now be 0.690. And again, we can calculate VOV using this formula. 0.690 minus 0.5, that will be 0.19 volt, and plugging in the current formula, it will be 77.6 microampere. So from 86, we have gone to 94.8 for plus, and we have come down to 77.6 for minus change. So the changes in both the cases, for plus 1, it is 94.8 minus reference hour 86, 8.8. And for the second case, it is 77.6 minus 86 is minus 8.4. So the changes is almost equal on both sides. And therefore, we can conclude that this is a linear amplifier. We conclude that the two changes are almost equal as indication of almost linear operation in the changes in Vg are kept small, when the changes in Vg are kept small. And this was just to give you an idea that we'll be solving problems in chapter number 7, small signal operations. So I hope you have been able to follow this. Please let me know through your comments. Thank you.